Hi, my name is Chris McKinnon. I'm a PhD candidate at the Dynamic Systems Lab at the University of Toronto, and this talk is about meta-learning with paired forward and inverse models for efficient receding horizon control. Robots are being deployed in a wide range of conditions. Some examples are shown here. This brings to light a number of key considerations that we must consider from a controls perspective. First, robots will encounter a variety of conditions. This means that it will be hard to model their dynamics ahead of time, so the controls approach must handle uncertain and changing dynamics. Second, many of these robots operate in conditions where the dynamics may change in repeated cycles. For example, a payload carrying robot may go from being loaded to unloaded. Robots operating outdoors may encounter a variety of weather conditions, and construction robots may be fitted with a variety of implements that change their dynamics. This means that multiple models may be useful for representing the robot dynamics over the course of its lifespan. Finally, since robots are exiting environments designed for their exclusive use and entering environments shared with people and other infrastructure, safety is a key consideration. One way of incorporating this is stochastic MPC is a controls. Stochastic MPC makes use of in SMPC. The computational cost of the dynamics model is a particular consideration. That's because the dynamics model is evaluated more often than the control input is applied to the system. So if we have a ground robot here performing a path-following task, SMPC tries to optimize a sequence of control inputs to minimize a cost function over a prediction horizon. Suppose that we want to apply a control input at 10 Hz. SMPC will start with some initial guess as to what the control input should be, and the predictions over the horizon may look something like this, the sequence of red dots. It may take a number of iterations for the solver to converge to the optimal solution, so we may end up evaluating the dynamics model more times before the solver converges to the optimal solution. This means that for our 10 Hz control loop, we're evaluating the model at 900 Hz. So that's because for each control input, we have to roll out a 30 time step prediction horizon, and we have to do that 3 times in order for the solver to converge. So it's really important that the dynamics model is computationally efficient. However, oftentimes the computational efficiency and the expressiveness of the dynamics model are at odds. So we have to, if we're learning the dynamics model directly, we have to trade off these two things. The main idea of this paper is to combine 2 ingredients to improve the performance of stochastic model predictive control. First, the expressiveness of a model, or how complex a function it can represent, is often a trade-off between that and computational efficiency. So more expressive models tend to be less computationally efficient, and as they get more computationally efficient, they tend to lose expressiveness. So in order to address this consideration, we leverage paired forward and inverse models to move the computationally expensive component of the model out of SMPC. So essentially, we're trying to take an expressive model and make it computationally efficient. The second trade-off is that as models get more data efficient, they tend to get less expressive. Data efficiency is the ability of a model to adapt to changes based on relatively little data. And to address this trade-off, we borrow ideas from meta-learning, which is geared towards making expressive models data efficient. The way that they do this is, for example, learning a set of basis functions offline that can enable fast adaptation to change online. The basis functions can be learned using expressive function approximators like deep neural networks, and then linear regression can be used to adapt to changes. Since neural networks are expressive and linear regression is data efficient, these models end up getting the best of both worlds. Our contribution is to combine these 2 ingredients for SMPC, so we can have data efficient models that are also expressive, and these expressive models are also computationally efficient. Our approach can be outlined as follows. We represent the system dynamics in the following way, where we partition the state into 2 components. First, we first group of states S, for which we know the dynamics, and the second state Xz, for which we don't know the dynamics. Intuitively, S may be something like position, where if we know the velocity represented by Xz, then we just have to integrate, so there's nothing to learn here. However, we might not know how the control input U is related to changes in the speed. So although knowing velocity, we can get position, we don't know how to relate the control input to the change in speed. We assume that the unknown dynamics have the following form. So they're a linear combination of an unknown function f prime and a set of known basis functions which only depend on the state phi. We also include eta here, which is additive Gaussian noise and represents model uncertainty. In an offline learning phase, we learn the entire right-hand side here with a function approximator f, and the output of that function approximator f, xz.f, is called the input feature. We also learn an inverse for this function in the second line, and that predicts the control input that generates a particular value of the input feature. The model used in SMPC is then what's shown on the right, and the key is that we've essentially replaced the unknown function here with the value of that unknown dynamics, which we learned using f. But what's important is that we don't actually evaluate f or any function approximator for f prime when we're doing optimization in SMPC. SMPC only optimizes the value of the input feature, and that is then converted back into a control input using the inverse input feature function. We can continue to learn the weights W online to adapt to changes in dynamics in a data efficient way, as well as quantify model uncertainty by learning the variance of the random Gaussian variable eta. In a block diagram, the approach looks like the following. So components learned offline are shown in orange and consist of the inverse input feature model, F inverse here, which takes the optimal value of the input feature and converts it into a control input that we can apply to the system. In addition, we have the forward input feature models. So if we have access to multiple data sets ahead of time, we can train multiple forward and inverse input feature model pairs and choose between them online. So we need to keep those around. And in those, the key is that those are evaluated at 10 hertz, which is only the rate that the control input is applied, rather than the rate that SMPC is doing optimization. The components that are learned online are highlighted in pink. So that includes the weight for the linear model here, as well as the variance of the additive Gaussian noise. In addition, if we have multiple input feature model pairs, we can select between them online using a mode ID block that estimates which input feature model is the best, given recent measurements from the robot operating in the relevant conditions. Again, the dynamics model used in SMPC that's evaluated at its high rate is the one shown here, which doesn't involve any expressive function approximators we use to learn unknown dynamics. This means that f and f inverse can be learned with very expressive function approximators because their computational efficiency doesn't matter as much. We conducted our experiments on the ClearPath Grizzly shown here, which uses a stereo camera for localization. We compared 4 variants of our approach, which differ in whether or not they use a learned input feature and whether or not they adapt the linear model parameters online. The first variant, denoted by BLR, stands for Bayesian linear regression and uses the control input directly as the input feature. This is the special case when the forward and inverse input feature models are identity. BLR adapts the linear model parameters online. The second approach is the complement, so we use a deep neural network to learn the forward and inverse input feature models, and we don't adapt the linear model parameters online. We hold them fixed. The third approach combines these two things, so we use a deep neural network to learn the input feature model, and we adapt the linear model parameters online. Finally, we show how to automatically select between multiple input feature model pairs using the fourth approach called which stands for multi-model. And that's going to choose online between essentially the BLR-DNN approach and the BLR approach. The results from the paper can be summarized in the following slide. In this figure, the y-axis shows the cumulative cost to traverse the path using the SMPC cost function. So lower here is better. On the x-axis, we can see each marker here is an independent traversal of the path. So we conducted 3 traversals using each method to model the robot dynamics. And we can use this to compare the impact of each component of the algorithm. So going from BLR to BLR-DNN, we are learning an input feature model, and we see a significant improvement in performance, which is reflected in the reduction in cost. Going from DNN to BLR-DNN, we are learning the linear model parameters online, and we also see a consistent improvement in performance. So both learning the input feature as well as adapting the linear model parameters online improves performance. Finally, using online input feature model selection, we can recover the performance of the best performing input feature model pair. So the algorithm is automatically able to identify that BLR-DNN describes the robot dynamics the best in this particular scenario. What's important is that using the learned input feature model, which is the computationally expensive component of the algorithm, adds only 4 to 6 milliseconds to the control loop, which has a 100 millisecond period. This computational cost is independent of the prediction horizon length, which is good because for SMPC, generally we want to have long prediction horizons. In summary, in our paper, we present an approach for model learning specifically tailored towards stochastic model predictive control. Our approach is based on the idea of combining paired forward and inverse models with meta-learning to improve closed-loop performance of the controller. Paired forward and inverse models are used to improve computational efficiency, which allows us to use expressive models to capture the robot dynamics. Meta-learning is used to improve data efficiency, which allows us to adapt to changes quickly. Together, by combining these two ideas, we showed that it was possible to reduce the cumulative closed-loop cost to traverse the path by up to 60%. Details, please check out the paper, which is available at the following URL. Thanks for listening. That concludes my talk.